Okay, just to highlight the steps that we took to find the necessary information to find the width and the height, because what we're going to do here, we're going to put it into a formula that we're going to see today. But I want to kind of talk through those steps that we did, and I can refer back to them when we do today's lesson. I think it'll make it a little bit easier with that formula if we can kind of remind ourselves all the steps that we're taking. So this is 27 from your homework here. It says use 6 rectangles for 2x squared minus x minus 1 between 2 and 5. Your a and b is 2 and 5. Your n is 6. So you know that from this information. There's really no need to look at the graph, because if it's just left endpoint, if you can find all your subintervals, then you're just going to take the left endpoint of each subinterval. If it's the right-handed rectangles, then you're just going to take the right subinterval. There's no need to worry about which, whether you're choosing upper sum or lower sum. So first thing we do is we find the width, right? Width is b minus a over n, 5 minus 2 over 6, 3 over 6 is 1/2, and then we take that 1/2, and then we go and find the next interval over, right? You start at 2, right? And you add 1/2 on your own. So 2 plus 1/2 is 5 halves, 6 halves, 7 halves, 8 halves, 9 halves, 10 halves. We reach the end. We should arrive at B, and we do if we add correctly and if we find the correct width. And then we have these 6 subintervals, right? 1, 2, 3, 4, 5, 6. And then if I want to do a left-handed rectangle, I just simply pick the left x value to plug into the function to get my height. And here I factored out the 1/2 because all the width is the same, but it's really 1/2 times f of 2, right? Width times height, plus, and then 1/2 times f of 5 halves, plus 1/2 f of 3, plus 1/2 f of 7 halves, right? And then all this it's just a matter of having to use the calculator, plug 2 into the function, get the y value. So it's tedious, but it's not hard, right? Hopefully we understand that process and it doesn't feel like a hard process. It's just tedious, especially if you have a bunch of rectangles that you have to find the x value and plug in the calculator and get the y value. But here, the left-handed rectangles is 55. The right-sided rectangle is 74.5. And the reason that's the case is because the graph is rising. And if it's rising, then the right-sided rectangles will always be over approximating than the left-sided rectangle. Just want to point that out. Okay, so that was the process yesterday. We're going to see something similar today, but any questions about that? Okay.
Is that like the method this is like to draw just the rectangle at the bottom?
Right, but here we don't even have to draw the rectangles. As long as we have all of our subintervals and x values and the function, we can just go ahead and build our left-sided rectangle without having to worry about which one is higher or lower.
We can from now on just like do the bottom.
Yeah. Yes, but if it's asking for upper sum or lower sum, then you will have to look at the graph to see which one is higher. Right? But if it's left-sided or right-sided rectangle, there's no need to look at the graph, right? All you need is left endpoint, right endpoint, number of rectangles, and the function.
You said a majority of them we're doing are like left side.
That's right. Your majority is going to be left and right-handed. Pretty much all of it. Yeah.
And on the quiz and test, are you supposed to make our own graphs?
On the quiz and test, you're not going to have to do you're not going to have to graph. Yeah. Okay, but yeah, question.
So if it's just giving us like the graph, like if it doesn't show the graph,
yeah,
it's not going to ask for upper or lower.
Right.
Like,
right.
Okay.
Yeah, that's right. Good. Any other questions? Okay. All right, so I want to make sure that we're clear on this before, because I'm going to refer back to this process a lot when we talk about the formula that we're going to do today. Okay, so, all right, so let's go to page 9. Okay. So let's say instead of just using 3 or 4 rectangles to approximate the area under the curve, let's say we're able to increase the number of rectangles from like 4 to 8. Do you think that will improve or not make much difference in terms of the accuracy? What do you guys think?
You what?
If we increase the number of rectangles from 4 to 8 to approximate the area of a region,
Oh, it will improve.
it will improve, right? Because if we have more rectangles, then there's going to be less gaps that because of the change in the graph, there's less gaps that's showing up in the graph, right? So what if we went from 8 to 16 or 16 to 32, 32 to 64? The approximations should improve. So what if we were able to go out to infinite number of rectangles?
To be exact.
Then that's the hope, right? That if we can follow that logic, then if we have infinite number of rectangles, then all the infinitely thin rectangles will adapt to all the different changes to the curve. So we're going to use that concept to help us move towards finding the exact area under the curve. Is we're going to use that concept of limits, and we're going to push the number of rectangles out to infinity, and we'll use limit as an approach to infinity, like how we did the first day in terms of the concepts there, in terms of comparing degrees. Okay. All right, so that's the idea here. Okay, now this is the long way of doing things. We're gonna have a much more efficient way of doing things in the latter half of unit 4 of this unit. But I want to start off by talking about the exact area. Everything that we did on the first day is now going to kind of make more sense in terms of, why did we do the summation notation? Why do we do the limits as an approach to infinity? Why do we do all those adaptations of formulas? This is where it comes into play. Okay, so this is the formula that we're going to talk about. Okay, now we talk about how every area has a width and a height component, right? And this here is my width component. And this here is my height component. Okay. I know it looks really messy because you have a bunch of variables here. Rather than saying, oh, 3 times f of 3, it's in this messy formula, right? And this b minus a over n, that should make sense, right? We did that in class, where b minus a over n can get us to that width. But here, it's leaving that flexibility in order for this formula to push the number of rectangles out to infinity. It's not settling on just one value, right? It's not saying, oh, just 8 rectangles or just 50 rectangles or not just 100 rectangles. It's saying n rectangles. And then once we have that as a variable, we can push that number out to infinity. So it's leaving that formula there, but we understand that every rectangle has a width component. Now the height component is in this here. It's f of a plus b minus a over n times I. Now we talked about previously how we did all this by hand, right? We found the width, right? We found the width, and then we manually added the width ourselves, right? 2 plus 1/2 will give us 5 halves. 5 halves plus 1/2 is 3 halves, gives us 3 plus 1/2, right? So now this is kind of like an engine that is doing all that work for us. It is finding the next interval. It's starting at the left end point. It's adding the width, and it's going to keep adding the width until it gets the next term. And that next term is going to represent the height. It's going to get that width and height, and it's going to move on to the next width and height, right? Now, we did it all by hand, but now this is going to, once we get into this formula for the particular problem, the formula will do all the work for us, okay? But we just have to kind of get the pieces in place and then let the engine kind of do its work. But okay. But I'm hoping that that makes sense, right? Rather than writing out every term by itself, the width and height is all built into this, and then all the width and height that we're going to add together is all going to be taken care of within this formula. Okay. So let's go through example 1 here.
That'd be given to us.
Yeah, I will. It says find the exact area between our function 4 minus x squared and the x-axis from -2 to 2. Okay, so we're not going to, we're not saying, oh, just use 4 rectangles or just 50 rectangles or just 5 rectangles. We want to use n rectangles and then push n out to infinity. Okay. So first things first, let's find the width. Okay, what's my a and b value? Yeah, -2 and 2, right? And then my n is going to stay as n because we don't want to force it into just a number, right? We want to let it have that flexibility to change. Okay, so my b minus a over n is just 2 minus a -2 over n. We're going to leave that n there. So 4 over n, that's the width. That's my variable width that I'm going to, sometimes before it was like 1/2 or 1/3 or 2. Now it's just 4 over n because we want that flexibility to push the number of rectangles out to infinity. Okay. So that's the width component. Now we're going to build out the height component here. Okay, so the height component is f of a. What's my a value? -2. Okay, f of -2 plus b minus a over n. That's my width. What's my width now? 4 over n times I. Okay, so this is the formula that will get me to each of the heights in function notation. Before it was like f of 2, f of 3, f of 4. Now it's all held within this f of -2 plus 4 over ni. This I will increment to the next value over rather than us doing it by hand. Right. Okay. Now this is only function notation, right? We want to get it in terms of what we want to use for our function. So we're going to insert this into our function, right? And then we can go back to the formula and put everything in place. Now, I want to make sure that we understand where this goes. This is not going to go before or after the function. It's going to go into that x variable. So to help us so that we don't put it in the wrong place, I want you to do this. I want you to write the function out. Okay. Now I want you to write the function with the x removed and the parentheses around the x. Okay. We want to leave a reserved space for our argument. That makes sense. We're taking the function and we're removing the x because we want a new argument to insert into the parentheses. Okay, are we good from here to here? Okay. If you can do this, then you're not going to put the argument in the wrong place because it's going to go directly where you have those reserved spots. Now, place the -2 plus 4 over ni into those spots. Okay. Okay, so now let's go back to our formula here. We have our width, we have our height components, and now we're going to put it into that limit notation, and then we're going to do what we did on the first day of cleaning it up and doing all the things that we did. Okay, so now here's our next step. Okay, I'm just copying the formula that I have above. My width is 4 over n times my height component, which is now 4 minus -2 plus 4 over ni squared. Okay. Width and height. So we're going to do what we did on the first day. We're going to FOIL all this out, clean all this up, get our summations rules to come into play, get everything in terms of n, and then we'll do limit as n approaches infinity. and then compare degrees and get all of our fractions, and then we can add them together. Okay, so first things first here, I'm going to focus on trying to fold this out. Okay, clean up. I'll drop the parentheses, distribute the negative through, combine like terms there. The 4 minus 4 cancels out. Distribute the 4 over and through. So 4 times 16 is 64. And now we want to break them down into individual summations, pull out the coefficients, and then use the summation rules that we have in place. So I'm going to start separating them. Okay, we have specific rules in place for these, right? We talked about on the first day, we can box these off and replace them with the rules that we were introduced to on the first day. We know summation I is just n times n plus 1 over 2. Summation I squared is n times n plus 1 times 2n plus 1 all over 6. And now we're going to involve the limits, clean some things up, and we only care about, within each fraction, we only care about what? What degrees do we care about? The highest one, right? Anything that's lower than the highest one within each fraction is not going to matter. So if I distribute the 64 through, I don't need this 64n, but it's not too hard, so I'm going to leave it alone there. I know that the result of this is just 64 over 2, right? I know that the limit of this fraction is just going to wipe this term out. Now, the second fraction, it looks like a lot to FOIL out, right? But again, I talked about the shortcut, how we don't care about the lower degrees, so just identify the first term of each part, multiply that out, and that will produce your highest term with the highest degree, and everything else is just going to be, it's just going to go away. All right, so 64 times n times 2n, that gives me 128, right? I'm going to put ... to show that there are more terms, but we don't care about them. So now we're just down to 2 fractions, right? And whatever those 2 fractions are, that will give us the exact area of this region. And it's no longer an approximation. We can actually get the exact area of what's underneath the curve. Okay, I know this is a tedious process, but I'm looking to see that you're able to understand this process, right? And if you make a mistake, it's not all or nothing, right? I'm going to give a lot of partial credit. If you make a mistake somehow, but I see that you still understand the process, I'm going to give you majority credit points. I care more about that you understand the process, not wait, you forgot to distribute a negative through and that messed up your whole answer, so the whole problem is wrong. Okay, so I care more about that you understand the process, that you set it up correctly, more so than all the messy parts of this problem. Yes.
How do you like get the final fraction? Like, how do you know that 3 is the highest? Like, where'd you get the 3?
Right. Okay, good. So a question is, how do we know what the degree of that first term is? We know that if I pick out the first term within each part, that will get me the highest degree, because any other thing is not going to produce anything more than a degree 3, because 64 times n times 2n will give me 128 n to the third power, because I have n times n times n. And if I were to fill everything out, I'm going to get a term with n squared. I'll get a term with n. I'll get a term with constant. But those things are not going to matter because I only care about what's attached to the n cubed. Because if I'm doing limit as n approaches infinity, I only care about the ratio of the coefficients from the highest degree. Okay, if we have time, I want to do another practice one of this, but let's do, I want to talk about one more approximation, and it's using trapezoids. So this is also a big part of approximations. So the two shapes that you're going to have to be responsible for when you're approximating an area under the curve is rectangles and trapezoids. Okay. So trapezoids, it's just going to be naturally a better approximation than inscribed rectangles, circumscribed rectangles, midpoint rectangles even. So trapezoid is where we approximate the area of a region using areas of trapezoids. Now, you may be more familiar with a trapezoid that is drawn in this form, where trapezoid is where you have a pair of sides that's parallel to each other, and then you have the vertical components that does not have to be parallel or congruent. Right? You just need one pair of parallel sides. Now, if I were to take that trapezoid, okay. Now, normally the formula that we use for that is base 1 plus base 2 times 1/2 height. Okay, but rather than that, what if we were to take this shape and flip it on the side? Okay, imagine taking that trapezoid and flip it on the side so that your vertical sides are parallel, and then your base is horizontal, and then your height or your the other side here can be diagonal. Okay. So if we want to think about a trapezoid in this perspective, then the area is going to be base over 2 times height 1 plus height 2, or 1/2 width times height 1 plus height 2. So I'm going to use this one here, and this is going to be the one that allows me to write it out without having to stare at a fraction, if I can just push that coefficient down in front.
No, that first trapezoid is 2 bases. So like I know in the equation there's only 1 base in there. Would you just take the average both of them?
So here we don't care about this upper part. All we care about is the horizontal base and then the height 1 and height 2. That's all we need to get to the area of the trapezoid.
So that first trapezoid, you know.
Yeah, so we're not going to use this orientation. We're going to use this orientation because all the trapezoids that we're going to see is going to look like something like that. The bases will be horizontal. The heights will be parallel, and then this part will be diagonal either one way or the other. Okay. So I want to kind of draw this diagram out again. And what if you look at just the way a trapezoid is shaped, right? So let's say I have my 6 subintervals here. 1, 2, 1, 2, 3, 4, 5, 6. Now a trapezoid is simply going to connect from the top to each other, right? Now, if you look, this curve only has 6 trapezoids, but if you look at how well the trapezoid is going to match the, it's already going to do a really good job of matching to the shape of this graph. And there's only going to be a minuscule amount of gaps between the graph and the geometric shapes of trapezoids, right? So that's what's so nice about trapezoids, is that it gives us a really good approximation, much better than rectangles, because the way rectangles are shaped, it has that corner that's always going to stick out. But trapezoid is just going to do a much better job. Even if we're just dealing with a few trapezoids, it's already going to match the shape of the graph a lot better. So I want to first convince you that trapezoid is going to be the best approximation. And then the second best approximation is going to be your midpoint rectangles. And then after that, inscribed or circumscribed, or left-handed or right-handed. But the sometimes on the AP exam, they will ask you to compare what is more accurate. And Remus, amongst geometric shapes, trapezoid is number 1, and then number 2 is going to be your midpoint rectangles. Okay. Okay, so we're still going to find the width the same way. So here, this function, I know I didn't tell you here, but the function goes from 0 to 6. Okay, so that's my a and b value. So my width is just b minus a over n. I still use the same formula for width. So 6 minus 0 over 6, which is equal to 1. So starting from my left endpoint, I'm going to keep incrementing by 1 until I reach my final point. And my area is simply going to be 1/2 width, height 1 plus height 2. Now, there are 6 trapezoids here, so we're going to have to do this 6 times, okay? Now, we see trapezoids here, but what do you see with 1 and 6 here? Triangle, okay? But we don't have to worry about it, because if it's a triangle, the formula will adapt itself into the triangle formula without us having to adjust it, okay? So if this side is 0, it'll just naturally turn into a triangle formula. We don't have to worry about, oh wait, I have to adjust it because that's different shape. It'll work itself out. So area is 1/2 width. Let's do the first trapezoid or triangle first. What's my width? 1. And let's leave it in function notation. F of what? What represents the height of my first shape? F of 0 plus f of 1. Now, technically, f of 0 is 0, and so this will naturally turn itself into 1/2 base times height, which is a triangle, but it's okay. We can just leave it as trapezoids. Plus 1/2 width. What's the second trapezoid? Yeah, f of 1 plus f2. So it's not hard. It's just a little tedious with all these trapezoids here. Okay, so we're just going to go down the line here, right? Okay, on the quiz or test, it won't be as messy as this. I won't, give you like maybe 3 or 4. Won't make you do 6 trapezoids here. Okay, and the rest is just plugging into the calculator, getting the heights from the function, and then adding them up, and it ends up giving us 35. So I just want to convince you here that your trapezoid, you're still going to require the same information. You're going to identify the width and height, but instead of making them into rectangle formula, you're putting them into the trapezoid. And then we just have to, I think the only thing that really trips students up with trapezoids is just having to memorize the trapezoid area formula. Okay, so it's 1/2 width times height 1 plus height 2. So if you think of it this way, it's very similar to a triangle formula. We just need to add another height component, right? We know triangle is 1/2 width times height. Just imagine, okay, I need another height there, so 1/2 width times height 1 plus height 2. Another issues that that I think students are gonna you're gonna potentially have later on when we talk about table of values is that for every trapezoid, okay, each trapezoid area only has 2 heights. Okay. I know that seems obvious right now, but later on, when you're going to see a table of values that span across a lot of different y values, the tendency is naturally students want to add up all the heights for that trapezoid. But every trapezoid is only going to need 2 heights. Okay, we're not going to add up all the heights for that region. We're just going to pick out the ends for that if it's just one trapezoid. Okay, any questions here? This feels a lot like how we would do area of rectangles. We're still going to find the width formula. We're still going to increment to find the heights, but instead of width times height, it's going to be 1/2 width times height 1 plus height 2. So there's always 2 heights associated with each trapezoid. Okay, let's see if we can squeeze in one more limit problem here. So this is on page 11 on a half sheet here. So let's try number 1. Okay, so we start off by building our width, right? What's our width going to be? Yeah, 2 over n, right? B minus a over n. I'm not going to replace n with a number. I want that n to have that flexibility to be pushed out to infinity. Okay, next up, let's build our height component. F of a, what's my a? 1 plus width times I, 2 over n I. Now that we have this in function notation, we have to insert it into this particular function, but we want to make sure that we can put this in the right place. So let's write the function out initially. Okay, we're going to adjust this function so that we know where to place the new argument. You're going to rewrite the function and remove all the what? Remove all the x's, because that is going to be your saved, reserved spot for that messy expression that you see there. Okay, so if you can get from here to here, you're not going to make a mistake with putting in your argument, because you know exactly, you're not going to put in the wrong place because you have a reserved spot for where that argument is going to go. So this is going to go here, here, and here. All right, does that make sense? Okay, so we do that. So 2 times 1 plus 2 over ni squared minus 3 times 1 plus 2 over ni plus 2. Now this should feel like day 1, where we just have to clean all this up, fold everything out, distribute the 2 over n, work in our summations, and then evaluate our limits. So if we can get to this stage, then I'm going to be a lot more lenient with partial credit, right? If you make a mistake after this, to me, that's not as important because that was just, if you're just adding or subtracting or forgetting to distribute negative through. But if you can get to this stage, then I know that you know how to set it up. Okay, and now you're just trying your best to get to your showing the rest of the work. But don't get stressed with, oh, I didn't get the right answer. I'm going to miss this problem. I'm probably going to give you the majority of your points if you just show me that you understand the process, right? Okay. Even if you get the wrong answer, I may still give you full credit because you're showing me each step of the way. Okay, so now we can FOIL this out. So make sure you don't just distribute the 2 through. You got to FOIL this out first before you distribute the 2, right? Okay. And I will provide you the limit definition. I'll provide you all the summation formulas. So don't have to worry about memorizing anything for this process. You have to know how to get from one step to the next. Okay, so order of operations, right? We don't want to do this. We don't want to distribute the 2 through and then square. That's not correct, right? You have to FOIL out these parentheses first, get all this resolved, and then you can distribute the 2 through. And don't forget, there's still this width component that we need to involve here, but right now I'm just trying to get all the height components cleaned up, and then I'll distribute the 2 over n through. Okay. Once you get to this stage, then it feels a lot more manageable because now I can start creating your summations, pushing out your coefficients, and then gradually move towards replacing your summation I or I squared or summation 1 with the summation rules. And then finally you can do your limit in front of that. Okay. Summation I squared has its own rule. Summation I has its own rule here. Summation 1 has its own rule. The goal is to get everything in terms of n so that we can begin to compare and work towards batching degrees and pulling out the coefficients. Okay, any questions about any steps?
You just keep it up for a few minutes. I'm sorry, I just switched.
Say again?
You just keep it up for like just a few more minutes.
Yeah. So I'll leave it up.
Great. Are you gonna practice this more?
You'll get some homework for practice, and then we'll spend some time next week practicing as well. Okay, so check your calendar for your homework. I'll send out a reminder on Sunday for me to check your homework on Monday. Okay, all right, don't get too cross.
Yeah. Such dangerous news, like. It's so low. Big flashing. The charger it takes. Yeah, I do, but I keep it. I'll show you tomorrow. I'll show you Monday.
It's about.
Okay, appreciate it. All right, I'll mark you down. Thanks.
That could be like a winner or home game for us.
I know.
And we beat them already, so they're gonna want to beat us.
Sundays, you find yourself more than just excited. You should call me.
No, I should go. They've been a lot more stressed lately.
Yeah.
Every game's been like a playoff for right.
No room for mistakes.
No, like the Bills games this year, like, and everyone's saying they're like sort of stressful. Everyone's saying, "Oh yeah, I'm gonna have a heart attack. I'm gonna switch." All like the crazy things that happen.
Yeah.
Like knowing that we against like teams that like we're like trying to be better than we always like keep them in the games.
Yeah.
They stick around.
Do you have any family members who are as invested as you with the Bills? Or
I do so. I'm fine.
yeah, you're probably the most. Okay.
Yeah. It's honestly just part of my personality now.
Yeah.
Yeah, I really hope they make the playoffs because it's the last game of the whole week. Oh, whole week of the whole season. We'll know if it'll be a winner or home game.
Yeah.
I hate Brad to have like we've made it so far from where we were and it's barely missed it.
Mhm. Yeah.
It's big because if we win, we get the 2 seeds. So like definitely try to win, even if we already clinched it.
That's impressive too. Be out of the playoff picture and all of a sudden
Yeah.
potentially be number 2.
So I think if we like even if we clinch a spot before, we should really try to win that game.
It's also good for your playoff momentum too.
Yeah. Because it means you get a home game for a longer game if you win that one, you get a number one.
Yeah. It's huge.
And like,
What
no, me too.
I've heard too is really good is that it's like 52% of fans in Miami are gonna be Bills people apparently.
He's like, they're going to watch them.
I'm surprised because I thought with the Dolphins doing so well that their fan base would be
Well,
growing.
this Bills mom is really good. You travel a lot.
Yeah, you travel well. Yeah.
Remember 2 years ago, like, I clicked the world and it's super real. That's really hard. Like, you were saying, explain.
I wonder which team has the most number of fans in terms of like nationwide. So Dallas. Oh, Chiefs. They've been doing so well recently.
In terms like, just like in general, probably.
Really? More than Dallas?
They're probably like. Patriot fans are going away thinking.
That's true. Patriots used to be big.
About time to got taste of medicine. It's like so beautiful had our last place. So wonderful. The Bills fan.
We got upgrade and get over.
It's been sweet, you know.
Interesting, yeah.
Yeah.
With double-digit losses, you know. It's great.
I wonder if Belichick will come back next
I
season.
don't think he will.
You don't
They're
think?
like he's talking with the owner, like, about his future plans.
Like, I'm.
He might go to like Carolina or something, I don't know.
I feel like if he stops, if he leaves, I feel like he's gonna retire. I don't think he'll find a better.
I think he's.
You think he'll still keep going?
His contract with Patriots is still for another couple of years.
Oh, really?
Worst combination of for people.
Yeah, I don't want to see it.
Every weekend, guys.
Thank you.
Thank you.
Hope we win.
They're just like,